All right, so today we're going to talk about something wild. It's a story about a tiny, tiny particle that for decades has had physicists on the edge of their seats thinking they might have to tear up the rulebook for the entire universe. So let's just get right to it. The big question here is, could one tiny particle completely upend everything we think we know about physics? At the center of this whole saga is this nagging feeling, this possibility, that our most fundamental understanding of the universe, well, that it's got a hole in it. And for a long, long time, one experiment has been Exhibit A in that investigation. So, that rulebook? Physicists call it the Standard Model of Particle Physics. And you have to understand, this thing is an absolute triumph. It's been called spectacularly successful for a reason. It predicts, well, almost everything about the tiny particles and forces that make up reality. And it does it with stunning accuracy. And there's always a but in physics, right? For all its glory, everyone's kind of known it's probably not the complete story. Okay, so meet the star of our show, the muon. The easiest way to think about it is like an electron's heavier, more unstable cousin. And the key thing, the property that makes this whole story happen, is that it spins. This spin makes it act like a tiny, powerful magnet. And when you drop this little magnet into a bigger magnetic field, it does something really cool. It starts to wobble, kind of like a spinning top just before it falls over. And this is where the mystery begins. Because for decades, experiments kept showing that the muon was wobbling just a little bit faster than the standard model said it should. This tiny time difference has a name, the G2 anomaly. Now you might think, a little bit faster, who cares? But in particle physics, a difference like that is a screaming siren. It's a massive clue that maybe, just maybe, there's something else out there, some unknown particle or force messing with the muon. So a clue like that, you can't just ignore it. This little wobble launched what has to be one of the most epic, painstaking quests in the history of physics. We're talking decades of work, scientists from all over the world, all focused on one thing, measuring that wobble with absolutely insane precision to find out if this crack in her understanding was real. The first hints actually popped up at CERN way back in the 50s and 70s, but things really kicked into high gear at Brookhaven Lab in New York. By 2001, they had a number, 3.6 sigma. That was a huge deal, a really strong signal that something was up. But to know for sure, they needed to be even more precise. And that led to one of the wildest road trips in science history. In 2013, they put the experiment's giant 50-foot magnet on a barge in a truck and moved it 3,200 miles from New York to Fermilab, near Chicago. A few years later, in 2017, the brand new, upgraded experiment was ready to roll. All right, so the magnet is in its new home, the experiment has been running for years, and the physics world is holding its breath. The year is 2021, and Fermilab is about to drop its first big results. Was this it? Was the anomaly real? Were they about to blow a hole in the standard model? The date was April 7th, 2021. The hype was real. Everyone was waiting for the announcement. And then came the number that made everyone's jaw drop. 4.2 sigma. So what on earth does 4.2 sigma even mean? Well, think of sigma as a confidence score in physics. To claim an official discovery, you need to hit 5 sigma. 4.2 is tantalizingly close. It means there's only about a 1 in 40,000 chance that this is all just random luck. You could feel it in the air. It really seemed like a discovery of new physics was right there, just within reach. I mean, look at what Fermilab themselves said in their press release. They declared that their results strengthen evidence of new physics. The chase felt like it was finally over. But yeah, this is where our story takes a hard left turn. See, making a super precise measurement is amazing, but it's only one half of the equation. You also have to be 100% certain about the number your theory predicts. And that's where things started to get messy. So, the problem is figuring out what the standard model actually predicts for that wobble. It's a wickedly complicated calculation. For a long time, the standard way to do it was a data-driven approach, basically using results from other experiments to help. But then came this new kid on the block, a method called lattice QCD. This thing is a beast. It uses some of the world's biggest supercomputers to calculate the value from scratch, right from the fundamental equations. And here is the heart of the plot twist. The new supercomputer-powered method gave a different answer than the old data-driven one. And the really crazy part? The new prediction was a much better match for what the experiment was actually seeing. Suddenly, the solid ground of theory turned into quicksand. The theorists were now arguing among themselves. Okay, so this created an incredible amount of drama heading into the grand finale. The Fermilab experiment had finished its run. They'd crunched all the numbers from 6 full years of data, and it was time to reveal their final, ultimate measurement. So fast forward to June 3rd, 2025. The Fermilab collaboration announces their final result, the culmination of an experiment that has spanned labs, states, and honestly, generations of physicists. And the number they landed on, the precision is just mind-boggling. They nailed it down to an accuracy of 127 parts per billion. That's like measuring the length of a football field down to the width of a human hair. It's an absolutely monumental achievement, even better than they'd originally planned for. And this is where it all lands. This chart tells the whole confusing story. That bar in the middle is the final, super precise experimental number from Fermilab. On the left, you've got the old theoretical prediction, and you can see the gap is still there, but it's smaller now. And on the right, that's the new prediction from the supercomputers. And our experimental result is sitting very close to it. So the huge, exciting fight between the experiment and the theory, it's kind of morphed into a fight between theory A and theory B. So, where does that leave us? Well, the simple, clean story of we found new physics, that's gone. Instead, we have something way more complicated, and honestly, maybe even more interesting. We have this rock-solid number from the experiment, but our two best ways of calculating what that number should be are giving us different answers. The hunt for new physics isn't over, not by a long shot. It's just taken a very weird, unexpected turn. And that's the cliffhanger. The exciting discrepancy got smaller, but the mystery actually got deeper. The theorists have their work cut out for them, trying to solve their own internal puzzle. Meanwhile, a whole new experiment is being built in Japan, at a place called J-Park, to measure this wobble with even more precision someday. It's just such a perfect example of how science really works, right? You set out to answer one question, and in the process, you discover a much deeper, more fundamental question you never even thought to ask.